Hello friends, today we will see second part of qualitative analysis. In this, we will see some precipitation equilibria. As we know, while performing inorganic qualitative analysis, many times we conclude certain results by presence of certain precipitate. For example, if we want to detect Cl minus, then in test tube we add AgNO3 and definitely AgCl will get precipitated, white color precipitation. And if suppose we want to detect sulfate ion, and in that we add barium nitrate, then we will get a precipitate of BaSO4. Again, it's a white color precipitate, and therefore it is very essential to study precipitation equilibria. But before going to the precipitation equilibria, we should know certain terms like solubility and solubility product. Then now we will see the term solubility. We know that many salts gets easily dissolved in a particular solvent like water, but many of the salt do not dissolve in a particular solvent to certain extent. They are called as sparingly soluble salt. For example, AgCl and BaSO4, they do not get easily dissolved in the water, and they are sparingly soluble salt in the water. And how will you define solubility? Solubility means amount of substance at a particular given temperature get dissolved in particular solvent to certain extent in its saturated level, at its saturated level. Yes, solubility also depends on temperature. On increasing the temperature, the solubility of particular salt in a water or in particular solvent get increased. Okay. After the solubility, there is one more term we need to study, that is solubility product. The unit of solubility is gram per dm cube, that is 1 gram of the solubility will be unity when 1 gram of substance gets dissolved in 1 dm cube of solvent. Then now we will see the term solubility product for sparingly soluble salt like AgCl or BaSO4. Now let's consider a salt MCO3, which is sparingly soluble salt. In water, it will produce M2 plus carbonate ion. Then by law of mass action, K will be concentration of M and concentration of carbonate ion divided by concentration of MCO3. On taking the denominator term to the left hand side, we get MCO3 into K is equal to concentration of M plus plus concentration of carbonate ion. As we know, MCO3 is a sparingly soluble salt. It will dissolve at too much low quantity, that is negligible, and hence its concentration in a solvent remains constant, and therefore KSP equals to concentration of MCO3 into K, and therefore KSP is nothing but concentration of M plus concentration of CO3 2 minus. Then how will you define KSP? It is nothing but at particular given temperature, it is a concentration of the ions of the salt raised to its power depending on its concentration. Then we will get precipitate only when the ionic product exceeds solubility product. That is, ionic product exceeds solubility product. That means the concentration, the multiplication of these two terms should be greater than KSP term. Then and then only you will get precipitate. And you know, in inorganic qualitative analysis, we can get the precipitate like on addition of AgNO3 inside Cl minus AgCl. But if suppose the multiplication of these two terms, that is KSP of AgCl is Ag plus and Cl minus. If product of these two terms do not exceed its KSP value, we won't get precipitate, and therefore the term solubility product play an important role in a precipitation equilibrium. Next up, we will see common ion effect. This effect is also an important term in inorganic qualitative analysis. As we know, there are certain weak electrolytes which have very low dissolving capacity in particular solvent. For example, AgCl dissolves very slightly, that is up to negligible amount in water. The degree of dissociation of weak electrolyte get decreased in presence of its strong electrolyte having an ion common with it. This is the definition of common ion effect. Let we see the term that explains this term. Consider NH4 OH. It is a base and it is weak electrolyte. It will dissociate very feebly in water. That is, the concentration of NH4 plus and OH minus ion will be very much less in water. Now let write its equilibrium constant K. K equals to NH4 plus the concentration of OH minus and concentration of NH4 OH. Okay. Since K is equilibrium constant, the value always remains constant at particular temperature. Now let add NH4 Cl, which is a strong electrolyte, dissolves completely in water and will produce NH4 plus Cl minus. And on addition of NH4Cl in NH4OH, see, NH4 plus is a common ion. NH4 plus ion is the common ion. And due to addition of NH4Cl, the concentration of NH4 plus increased, is raised, and it will affect the K value. But as you know, K is constant. It has to be maintained constant inside the solution. The numerator term has been increased due to presence of NH4 plus, and to maintain K constant, the reaction will get shifted backward towards left, and hence the dissociation of NH4OH gets suppressed. That is, the reaction goes in a backward direction. Why? This is due to presence of NH4Cl in NH4OH. That is, NH4 plus ion concentration increase, and to maintain dissociation constant, K value constant, the above reaction has to go in a backward direction. That is, dissociation of NH4OH gets suppressed. This is common ion effect. It has a huge role in inorganic qualitative analysis. How? Let's see. Now we will see a term, common ion effect. How it play an important role in inorganic qualitative analysis. Let's suppose you have been provided with mixture of two cations, that is Ni2 plus and Fe3 plus in a solution. On addition of NH4OH, that is, it will produce NH4 plus and OH minus. What will happen? This OH minus will get reacted with both of these two, producing precipitate of nickel hydroxide and ferric hydroxide, because the Ksp value of nickel hydroxide is 8.7 into 10 raised to minus 19, whereas Ksp value of ferric hydroxide is 3.8 into 10 raised to minus 38. If you compare these two values, then Ksp value of FeOH thrice is very much less, that is 10 raised to minus 38, whereas Ksp value of nickel hydroxide is up to 10 raised to minus 19. That is, this Ksp value is nearly 2 times lesser than that of nickel hydroxide. But if we take mixture of NH4OH and NH4Cl, the NH4 plus is common. It will raise the concentration of NH4 plus, results in decrease, that is suppression of ammonium hydroxide. This is the common ion effect. And due to that, only the Ksp of FeOH thrice will reach, because concentration is less. And due to addition of NH4Cl in NH4OH and mixture of this, we have to add in this two things, only ferric hydroxide precipitate will get formed, because we have suppressed the concentration of OH minus ion due on addition of strong electrolyte NH4Cl, and hence Ksp of FeOH thrice will only reach, and FeOH as precipitate will get formed, and nickel will remain in the solution form. And from this we can easily separate, we can easily detect Fe3 plus ion in presence of Ni2 plus. This is about the common ion effect, play a huge role in inorganic qualitative analysis. Next term we will see uncommon ion effect. As you know, uncommon ion effect, it is the opposite of common ion effect. What it says, that if you consider a salt like AgCl, we know it is sparingly soluble salt in water. It is sparingly soluble salt. But if we add some foreign ions which are not common, that is uncommon, that is on addition of KNO3 in AgCl solution, the solubility of AgCl increases. Why this happens? Due to presence of the foreign ions. Which are the foreign ions? K plus and NO3 minus. These are uncommon with AgCl, and this is nothing but the uncommon ion effect. They are also known as salt effect or activity effect. Why this happens? Because KNO3 increases the ionic strength of the water, and indirectly this helps to dissolve AgCl in water.